Hi everyone, here are your notes for section 5.3, which is getting us into some more identities. So if you've not yet started a list of all the trig identities that we've covered thus far, I would definitely go back and put in the ones that we have from our 5.1, 5.2 notes. So if you could just have them all on one sheet of paper, because you do have open note assessments, it might make it easier to have everything in one place at one time. Okay, so in this section, we're going to use formulas that involve sum and differences to verify identities. So here are 6 new formulas that you are now going to add to your toolkit. Our first one that we have here is our sum of sines. So the sine of alpha plus beta turns into the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Your cosine sum identity, so if we had the cosine of alpha plus beta, then that's equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. And then the tangent one is down here. We have the tangent of alpha plus beta. That's equal to the tangent of alpha plus the tangent of beta, all over 1 minus the tangent of alpha tangent of beta. Again, you don't need to have these memorized because you will have them available to you on a piece of paper. And then on the right side of our column, we have our difference identities. So the difference for sines. So sine of alpha minus beta is equivalent to your sine of alpha cosine of beta minus your cosine of alpha sine of beta. And then your cosine of alpha minus beta is equal to the cosine of alpha times the cosine of beta plus the sine of alpha sine of beta. So try to remember your sines and cosine. Your sines have sine and cosines next to each other. I guess I should have done a different color. And then so sine, cosine, sine, cosine, sine, cosine, cosine, sine. And then your cosines attach the cosines together. Cosine and then sine, cosine and then sine of each. Again, you don't necessarily need to have them memorized because you should be able to have them on a piece of paper sitting there in front of you. And then the last one is our tangent difference. So the tangent of alpha minus beta is equal to tangent of alpha minus the tangent of beta all over 1 plus the tangent of alpha tangent of beta. Okay, so you're going to want to make sure you get those written down on a piece of paper. So what patterns do you see that could help you to memorize these formulas if you were requested to memorize them? I would write something to the effect of that your sine keeps your operation when expanded. So if it was plus, it stays plus. If it was minus, it stays minus. Your cosine changes signs. So if it started out as plus, it goes to a minus. If it started out as a minus, it goes to a plus. Your sine alternates. Between your sine and your cosine. But your cosine is grouped cosine. So cosine is grouped, oops, I don't know where that came from, is grouped cosine, and then sine. Okay. All right, so now let's go ahead and start using them. So for example 1, it says find the exact value of cosine 70 plus cosine 40 plus sine of 70 and then sine of 40. So I clearly see that I have cosines attached together and sines attached together. So it's clear to see that 70 is my alpha and 40 is my beta. And because the cosines and the sines are attached to each other, that means it's going to be a cosine identity, right? And then we've got to decide, is it a plus or a minus? Well, remember your cosines always change signs, so this case would be a minus. So this really is the same as your cosine of 70 minus 40, which would be the same as the cosine of 30 degrees. And if we use our unit circle, our cosine, which remember is our x at 30 degrees, is root 3 over 2. Okay. In example 2, we're going to write the following expressions as the sine or the cosine of an angle. So here I have alternating sine cosines, right? So sine, cosine, cosine, sine. So I know that's going to be original sine. Sine carries the operation. So if it was a plus to start with, it's going to be a plus there. My alpha is 22. My beta is 13. So that just turns into the sine of 22 plus 13 is 35 degrees, which we don't know what exactly the sine of 35 degrees is. I could use my calculator to come up with that, but we'll just leave right there because it's just asking us to write it as an expression as sine or cosine. For B, we have cosines together, sines together, so that's going to be a cosine. Then we got to decide if it's plus or minus. Remember, cosines alternate signs. My alpha is pi over 3. My beta is pi over 4. So now I just have to think about what 1/3 minus 1/4 is. If I come up with a common denominator, that's 4/12 minus 3/12, so 1/12. So this would be the same as the cosine of a pi over 12. And again, we don't know exactly what that is. But we could use our calculator and put it into radian mode, right? And then type in cosine of pi over 12 and get a decimal interpretation of that. All right, example number 3. To find the exact value for the cosine of 15, we're going to use the fact that cosine of 15 is equal to the cosine of 45 minus 30 and follow the difference formula for cosines. So cosines, remember, keep your cosines and your sines together. So it's cosine of alpha, cosine of beta. Because it was minus, it's going to go to a plus, and then it would be the sine of alpha, sine of beta. So let's put it in context here. So the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the sine of 30 degrees. Now we should know all of these. So if I go from the unit circle, or we should know 45s, right? That's just going to be a root 2 over 2. My cosine at 30 degrees, we said it before, was root 3 over 2. My sine at 45 is root 2 over 2. And my sine at 30 degrees is 1/2. So when we bring that all together, we get, what, root 6 over 4 plus root 2 over 4. Oops, what has my root 2? And then I can put that into one big fraction of 4 over root 6 plus root 2, which I can't combine those together, so there we'll just leave it as is. Done. Yeah, I mean, I guess another way we could have factored out a root 2, and then that would left me with root 3 plus 1 all over 4. Same answer, right? All right, so now we're going to use the sum and difference identities to verify identities. So verify the following identity. We have the cosine of alpha minus beta all over the cosine of alpha, cosine of beta, and the right side is where we're trying to get to. So cosine of alpha minus beta, let's go ahead and convert that. That's going to go to cosine alpha, cosine beta plus sine of alpha, sine of beta. All right, all over our cosine alpha, cosine beta. Okay, so now I can split this into 2 separate fractions, right? And some of you guys lost points on your last quiz because you didn't show enough steps. When you are doing these verifyings, like if you guys remember back to your geometry days, you have to show every single step. You can't just kind of jump steps and go, oh, well, this is what this would end up to be. All right, so I'm going to break this into 2 separate fractions, each with a denominator of cosine alpha, cosine beta. So over here, that's just going to cancel out to 1. Over here, what are we left with? Well, we're left with a sine of alpha over a cosine of alpha times a sine of beta over a cosine beta, which aren't those tangents? Yes, now we're left with 1 plus the tangent of alpha, tangent of beta, which I think is where we need to get to, which is equal to 1 plus the tangent of alpha, tangent of beta, QED. Done. So we go over to example 5. I know it says to try on your own. If you want to try it on your own and pause, feel free, or just work through it with me. We have a difference for our sines. So remember, that's going to go to the sine of pi over 2 cosine of x. Sine carries the sine, and now it's going to be a cosine of pi over 2 sine of x, right? So you just kind of flip-flop. Here I had my sine attached to my pi over 2. Now over here I'm going to make my cosine attached to the pi over 2, right? And then where can we go from there? So now the sine of pi over 2, let's think about that. Sine of pi over 2, so that puts me up at the y-axis, so that would be 1. So this is 1 right there. 1 times the cosine of x is just cosine of x. So that becomes a cosine of x. And then your cosine of pi over 2, isn't that 0? It should be 0 times a sine of x, which is just 0. And cosine x minus 0 is just cosine x, which is equal to cosine x, which is where we were trying to get to, QED. Quadrate demonstratum, is that what it was? Something fancy like that. All right. Example 6. Find the exact value of sine of 5 pi over 12. And then here we're giving a hint. 5 over 12 is the fraction, same as 1/6 plus 1/4. So what we can do is we can break this into the sine. So that's going to be the same as the sine of pi over 6 plus pi over 4. Okay, and then if we take that and separate it, so that's the sine of pi over 6 times the cosine of pi over 4, and a sine carries the sine, so plus, and then we're going to do a cosine of pi over 6 and a sine of pi over 4. All right, so now using the unit circle, our sine at pi over 6 is going to be 1/2. Cosine of pi over 4 is square root 2 over 2. Plus cosine at pi over 6 is root 3 over 2. Times sine is pi over 2 over 2. Or sorry, root 2 over 2. So where does that get us to? So root 2 over 2 times 1/2 would be root 2 over 4. Root 3, root 2, so that's root 6 over 4. Combine that all together. I would just rewrite that as root 2 plus root 6 all over 4. That's the way I would write my answer. You may see some books factor out that root 2 and turn it into 1 plus root 3 all over 4. But this is sufficient in my book. For example 7, we're going to evaluate the cosine of 7 pi over 12 using the fact that 7/12 is 1/4 plus 1/3. So this is the same as the cosine of pi over 4 plus pi over 3, which is going to go to the cosine of pi over 4. Remember, cosines are together, so cosine of pi over 3. Change the operation to subtraction. And then the sine of pi over 4, sine of pi over 3. Cosine pi over 4, that's easy, root 2 over 2. Cosine at pi over 3 is going to be 1/2. So adjacent would be the 1. And then minus root 2 over 2 for my sine of pi over 4. And then sine at pi over 3 is going to be root 3 over 2. Combining that together gets me root 2 over 4 minus root 6 over 4, which gives me a final answer of root 2 minus root 6 all over 4. And I would just leave it there. All right, very good. Not too crazy, I don't think. All right, so now making a sketch to come up with all this. So suppose that we know that the sine of alpha is equal to 4/5 for quadrant 2 and an angle of alpha. And the sine of beta is equal to 1/2 for quadrant 1, where your angle is beta. Find the exact value of each of the following. Okay, so what we're going to do is we're going to first make a sketch of what these angles look like. So let's start with the alpha. So they're telling us that alpha is in quadrant 2. Small pen, there we go. So I'm going to make my reference triangle over here. I'm going to call this alpha. Here's my right angle. We know that sine is opposite, so 4 over 5. Using the Pythagorean theorem, 25 minus 16 is 9, square root it is 3. But it's also going to be a negative 3, right, because we're in quadrant 2. And then we're putting beta in quadrant 1. Here's my beta. And we're at 1/2, so 1 over 2, which puts that adjacent leg at root 3, using your Pythagorean theorem. Okay, so now, cosine of alpha. Well, we already have it set up. So cosine is adjacent over hypotenuse, so negative 3/5. B, cosine of beta, adjacent over hypotenuse, so root 3 over 2. C, cosine of alpha, cosine of beta. Okay, so that means we're going to have to do a cosine of alpha, cosine of beta, subtract sine of alpha, sine of beta. Well, cosine of alpha, we said was negative 3/5. Cosine of beta is root 3 over 2 minus sine of alpha is 4/5. Sine of beta is 1/2. So where does that get us? So here we have a negative 3 root 3 over 10 minus, looks like 4/10. So if I put that all together, I get negative 3 root 3 minus 4 all over 10. That's my one fraction. Do it for sine. So sine of alpha plus beta. So that would be the sine of alpha cosine of beta plus cosine of alpha sine of beta. So the sine of alpha is 4/5. Cosine of beta, root 3 over 2, plus cosine of alpha, negative 3/5. Sine of beta is 1/2. So we get 4 root 3 over 10 minus 3/10. So putting that all together gets us 4 root 3 minus 3 all over 10. That's our final answer there for D. All right, last page, example 9. So reduction formulas. So if one of the angles in a sum or difference is a quadrantal angle, so remember quadrantal means they would lie on the x or y axis. So at 1, 0, 0, negative 1, negative 1, 0, and 0, 1. I forget where I was at. Then the sum or difference identity yields a single-termed expression. Since the result is less complicated expression, the resulting identity is called a reduction formula. So we're going to prove the following reduction formulas. All right, so we have sine of x plus pi is equal to negative sine of x. So when we break that out, we have the sine of x cosine of pi plus cosine of x sine of pi. Well, the cosine at pi, remember cosine is our x, so at pi that puts us at negative 1. So this left chunk is going to be equivalent to negative sine of x. On the right side, cosine of x will stay cosine of x, but sine at pi is 0. So that whole thing just goes to 0. So negative sine of x is equal to your negative sine of x. QED. For this one, cosine of x plus 3/2 pi, we want to make that equal to sine of x. So that gets me the cosine of x, cosine of 3 pi over 2, minus sine of x, sine of 3 pi over 2. So cosine at 3 pi over 2. So that puts me down at 270, right? So on the y-axis on the bottom, so at 0, -1. So my cosine is 0. So that gets me 0 minus sine of x would put us at -1. So that would become a negative sine of x, which the negative of negative is a positive sine of x, which is what we ended up with. QED. Done. All right, now let's work with these tangent functions, our formulas. So for example 10, we're going to find the exact value of the tangent of 5/12 pi. Using the fact that we're going to have alpha be our 2 pi over 3 and beta being our pi over 2. Okay, so 2/3 minus 1/4 is what gets us to 5/12. So I'm going to be subtracting these. So the tangent of 2 pi over 3 minus pi over 4, now going right to that formula on the first page, means we're going to do a tangent of 2 pi over 3 minus the tangent of pi over 4 all over 1 plus your tangent of 2 pi over 3 tangent of pi over 4. All right, so tangent of 2 pi over 3, if you look over at your unit circle, that's going to get us a ratio of -√3. And then your tangent of pi over 4 is 1, right? So it becomes a -√3 minus 1 in our numerator. And then in our denominator, the 1 stays. And then we have the tangent of 2 pi over 3 we said was -√3, and tangent of pi over 4 we said was 1. So putting that all together gets me -√3 minus 1 all over 1 minus √3. Okay, but it's bad math practice, right, to have a radical in your denominator. So we need to rationalize the denominator. Rationalize, I'm running out of space here, denominator. How do we rationalize the denominator? Well, we multiply by the conjugate in this case, because I have binomial down here. So 1 plus √3, 1 plus √3. And then when you multiply and FOIL that out, we get -√3 times 1 is -√3. -√3 times √3 is -3. Then we get a -1, then we get a -√3. In our denominator, the middle terms are going to cancel out, and you're just going to be left with 1 minus 3. So combining that together gets us, looks like -4 minus 2√3 all over -2, which if I divide my numerator terms by -2, we get +2 plus √3. And there's your final example. That ends your notes.